Thank you very much, James. Thank you for the invitation. So indeed, I'm going to, the main focus of the talk is going to present this review that we did with Eric. It's available on the annual review website. It's not the definitive version, so there might still be a few mistakes in there. So first of all, a little disclaimer, we were only limited to 150 citations. So if you don't see your paper in the main text, maybe it's in the supplemental appendix, which has another 150 citations roughly. So, and other disclaimer, so for this talk, I'm going to be a little bit more partial than the review to give you my grain of salt. And so the objective of this review was twofold. So first, we want to present RV data analysis to non-specialists. So I put what I would like to, I would have liked to have as a grad student starting to work on the subject, and also to introduce the field to statisticians who might want to try advanced statistical methods. And the other objective of the review is, rather than giving solutions or state-of-the-art technique, is to pose the problem formally and try to determine what we are trying to do precisely. And in the second part of the talk, I will present my own work on an optimal exoplanet detection criterion. So, okay, so what is so there are different steps in RV analysis. So you start from the raw spectrum, then you can get to the one-dimensional spectrum. And from there, from the one-dimensional spectrum, you try to extract activity indicators. So for example, the full width half maximum, the bisector span, and then you have a few time series. So you have your time series of RV here, of bisector and of log R prime HK. And your next step is to model it. So typically you would use a Gaussian process, and you're trying to give a likelihood function of the data knowing the parameters of your model. And once you have all that, you're going to try to decide whether you have detected a planet, and if yes, with which orbital elements. And so the key ideas of RV data analysis are the following. So the first idea we can rely on is that planets induce a pure Doppler shift. So it will, if we have a planet, it will only affect the translation of the spectrum. But if we have, for example, a spot around the star, it will affect also the spectral shape. As the spot moves across the star, then the average spectral line here at the CCF is going to change. So our activity indicators, for example, the width of the line, the bisector, they are going to change as well. And the second thing we can leverage is that the planets have a periodic signal, except if you have very strong dynamical interactions between the planets. But stellar and instrumental effects, they are usually not strictly periodic. So we have the planets only in the Doppler shift, but within the Doppler shift, or the RV, which you think is your best guess as what the translation of the spectrum is, in that you also have contaminating signals which come from the star or from the instrument. So what we want is, first of all, an RV definition whose definition is as close as possible to the global Doppler shift. And this is not trivial, because if the shape of the spectrum is changing, there is no model-independent definition of what RV is. So, and the second thing we want is to use the shape information in the spectrum, the color information of the spectrum, everything that is not a pure Doppler shift, to predict what is the value of this contaminating signal. And also we want realistic uncertainties on this contaminating signal. So I think from here we can see this either as a statistical problem or machine learning problem. So you can try to learn you can try to learn sorry. Yeah, sorry. Yeah. You want to leverage the shape of the spectrum, so you can train your neural network of whatever machine learning method that you have to predict from this shape what is the contaminating signal in RV that you expect. Or you can try to have a joint model of the center of mass and of the RV contaminating model within a statistical framework. Okay, so if we want to try to formalize the problem in a statistical sense of these different steps, so let's say that we have planet parameters theta. This is what we want to learn about. We have other parameters, eta, which are, for example, the stellar rotation period and offset, everything that you want to determine other than planetary parameters. And at the beginning, you have a full data set, so you have your raw spectra. The first step is to say, well, I'm going to base my decision, my estimation of the planet parameters, not on the full raw spectrum, but on a set of reduced data sets. Typically an RV time series and a few time series, which are the activity indicators or indicators in general, not necessarily for stellar activity, but they are time series. So now this is a sort of compression problem or dimensionality reduction problem. So now you can expand this posterior distribution with the base formula, and then you have a likelihood and a prior distribution. And determining what is the likelihood, what is the prior, this is the modeling problem. So this is where we are going to put our Keplerian equations, our Gaussian processes, our offsets, trends, and so on. And based on everything that you've computed, you want to take a decision on the number of planets. And for that, you're going to use a periodogram, a false alarm probability, or a base factor, or other metrics. And for all these steps, there is also something very important that you need to take into account, that it's the numerical method, because you want the numerical method to retrieve exactly what you think it retrieves. So let's talk first about the reduction. So from the raw data to the data where we are going to start to search for planets. So in this picture, this concerns this step. So from the raw spectrum to the RV and the indicators. So I'm not going to talk about calibration, wavelength solution, how to get to the one-dimensional spectrum, because it's a subject on its own. And so in our review, it's presented briefly in the supplemental appendix. And so first, so from discussion with Christophe Lovis, it appeared that on this particular problem, error propagation is something which is very important and which is currently being implemented in some of the pipelines. So when I talk about indicators, I talk about the full width half maximum, the bisector span, but also principal components that come from the analysis of the time series of CCFs or spectra. Or you can also consider that your different time series of indicators are the spectra themselves, are the one-dimensional spectra. So, and the difference between the modeling aspect, which will be treated later, is that at this level, we are not considering that the signal might come from planets. The model of the signal of the planets will come later. So, yeah, so the first step is, once you have your 1D spectrum, you want to correct for residual effects that were not taken into account in the calibration step. So, for example, you want to perform a color correction, telux correction, correction of the moon, or other effects which come from the instruments like ghost reflections, fringing, and so on. And so the main takeaway point from our reading of the literature is, and discussion with my colleagues, is that we don't have to worry about only stellar activity. So there are lots of papers on stellar activity nowadays, but systematics are still a major source of uncertainty, and so it's really important that we get this right. So now you want to estimate the RV. There are several methods. So either you have a fixed mask and you convolve it with the spectrum. So F is the one-dimensional spectrum. You have template matching, where basically you make a first order Taylor expansion, or you can go a little bit further in the model and do forward modeling. So from cross correlation to forward modeling, you have more flexibility, so it's potentially more realistic, but you also have more degeneracies. So trying to find the right balance, the right rigidity of the model is going to be very important. And on this point, I think that it's probably, so experience will show, but it's probably best to estimate the RV and the contaminating signals at the same time, so RV and indicators at the same time, because then you can account for the shape change of the spectrum and try to determine what the degeneracy between the shape change and the translation due to the Doppler shift. So, and to compute these indicators, the classical way to proceed was to do it spectrum by spectrum. So in each spectrum, you compute either a global statistic, such as the width of the full of the spectral line, the bispector, the contrast, or look at a specific spectral line like H alpha or log R prime HK. So you can also consider the time series of CCFs or the time series of spectra and try to analyze these as a whole. And so I think analyzing the time series of the spectra is more promising because, as you can see here in the paper from Criterion 2021, so what this plot is basically each row is one spectrum taken at a different time. So you stack the different spectra taken and you can see very clearly that you have patterns, and these patterns, how they move, is something that you can, I think, better estimate, better see if you look at all the time series, the whole time series of spectra. So in the Express challenge, there have been several ways to extract activity indicators from these different time series, either CCF or spectra. And I noted that usually it's based on having a non-linear transformation or linear transformation of your spectrum, and then you apply a principal component analysis. And so there are many different results depending on the method that you use. And so I think we need, so in the Express challenge, I mean, there have been very different results depending on your RV correction method. So I think the idea of trying something, you pick a transform, and then you do a PCA, and thanks to the theorem of wishful thinking, it's going to correlate with the RV. Not sure it's going to bring us where we want to be. So yeah, now let's move to the modeling part. So we want to model the contaminating signals and the signal coming from the planets at the same time. And one of the crucial problem here is what is the model we use for stellar activity. So the classical model is that you have your radial velocity time series, you model it as a sum of Keplerians, plus you have a stochastic term, and this stochastic term is going to be Gaussian. So basically your data is, your RV time series is modeled by a likelihood which is Gaussian and which has this form. And the parameters of the noise are going to be taken into account in the definition of the covariance matrix of the Gaussian process. But before going to the Gaussian process, we can say, well, actually, maybe we don't need to go into that much detail. And the first model is to say, well, the activity or the contaminating signals are just going to be a linear combination of our indicators. So this is a method which worked well in the RV fitting challenge of Xavier Dumusc, but I think it worked unrealistically well because the correlation between the bisector and the RV, or the log R prime HK in the RV that you get with SOAP is, to me, compared to real data, it's much too high. And the problem you have also is that the indicators that you get, they are noisy. So if you have this linear model, it's not really easy to propagate the uncertainty that you have on these indicators. And furthermore, we know from the sun, from other stars, that there are phase shifts or closed loop behaviors between indicators on RV. So it means if you plot the indicator and the RV, you will have a sort of a figure which closes on itself. So if we want to account for the stochastic nature of the noise and something less rigid than a linear model, you can use a Gaussian process. And a Gaussian process is either characterized by its kernel, because we assume, obviously, that the mean of the noise is 0. So now we want to compute its autocorrelation, so its kernel. But characterizing the kernel is equivalent to characterizing the power spectral density, so the squared modulus of the Fourier transform. And so now we have several type of stellar noise that we want to model. So the effect of spot and faculae, the granulation signal, and the oscillation signals, the P modes, which for extreme precision radial velocity is not negligible. And then there are several kernels which have been proposed, for example, the quasi-periodic one, which you see in purple here, or quasi-periodic cosine in yellow. And the difference between the two is that the quasi-periodic cosine accounts for the fact that you typically have spots which have a phase shift of 180 degrees. So you see one spot, and half a rotation later, you have a spot roughly at the same location. And so you see that the behavior is quite different, because in one case, there is never an anti-correlation in the GP, or there might be one. You have another type of Gaussian process, which is often used, which is the stochastic harmonic oscillator, which has a key advantage. It's when you use it, when you evaluate the likelihood where you need to invert the covariance matrix, the cost is linear in the number of data points and not n to the power 3. And also, you can use a Matern 3-2 kernel to model the stellar activity. And in particular, if you modify it a little bit, you can account for magnetic activity when the spots are short-lived. Because if the spot lifetime is below the stellar rotation period, then you wouldn't see a peak of correlation one stellar rotation later. And finally, in Luger 2021, you have physically motivated kernels. They are developed for Doppler imaging, but I believe that Rodrigo is working on their application to RV. And so in that case, we would have a kernel which is not defined with ad hoc properties, with qualitative properties, but with quantitative physical quantities. Okay, so for granulation in particular, something that seems to work well in RV and also in photometry is the so-called super Lorentzian profile with a decay to the power 4. So this is the power spectral density, and it seems to decrease with the power 4 of the frequency. And the advantage of this kernel is that it has accelerated representation, so you can use an efficient numerical method to compute it. And for the granulation, the conclusion seems to be that you need at least 2 different timescales, so 2 different super Lorentzians with a free amplitude and natural frequency. Okay, so the problem with the Gaussian process, if you analyze only the RV time series, is that the Gaussian process is the square modulus of the Fourier transform. So you have no phase information. But what you want to do, what you want to know is what the value of the contaminating signal is at a particular time, not on average, but at this particular time. So you want to use the information from the shape indicators of the spectrum, like the bisector, the log prime HK, and so on, to predict, well, this contaminating signal value is this at this particular time. And so if you train your Gaussian process on the activity indicators, and it's going to give you the hyperparameters, well, the hyperparameters give you the average properties of the process. And it's so the detection limits that you will have with this method are probably overly pessimistic. So let's model RV and indicators jointly. The first model to do so was proposed by Rashpal 2015. So you have the RV, which is a linear combination of the Gaussian process and its derivative. And then you build also a Gaussian likelihood, just like before, but now instead of having just the RV as the data, you augment your data. You take the RV, then you concatenate with the vector of log R prime HK and bisector, and then you have a covariance on this augmented data. And the rationale of using the derivative, or why I think it's useful, is that if you have a phase shift, which is known to happen between RV and indicators, then you can model them with well, there's a derivative. There is a delta t missing, sorry, but basically the delta t is going to be the coefficient of your derivative here, multiplied by the amplitude of the signal. You can generalize this model by saying that now your radial velocity and your indicators in arbitrary number will be modeled as a linear combination of the Gaussian process, its derivative, its second derivative, and a Gaussian process which is specific to this particular indicator or RV time series. So to illustrate why it can be advantageous to proceed like that is here is the example of TOI 178. Here you have the RV, the bisector, and the log R'(HK). And you see that when you look at the maximum of the RV, so in yellow here, you have the estimated contaminating signal from the star. The peak is reached before in the RV than in the bisector, and a little bit before than the log R'(HK). And this is the case both here and here, which indicates that at least on this period, there is a phase shift between the activity indicators, and you can account for it with the derivative model. But the thing is, when you look at images of the sun, the evolution of the spot where how the facula spread, the magnetic network, the granulation pattern, it seems unrealistic to me that we can grasp all this information just with a stationary Gaussian process. So I guess there is still work to be done to calibrate our models on the sun, to leverage everything that we know on stellar physics and try to test whether we can see this behavior in the sun, and more importantly, try to derive practical analysis method from the knowledge of the physics. So the other part of the model that you have to define is the prior. So especially if you want to compute the Bayesian evidence, you need to compute this term here. So the probability distribution of the orbital elements and the nuisance signals before seeing the data. So in the review, Eric did a very nice table of reference priors. It's in the supplemental appendix, and where he discussed what are the pros and cons of each different priors. There is another emerging trend, which is to exclude unstable planetary configurations, because then you know from physics, even before looking at the data, that certain configurations cannot have a lifetime which is too small to be observed in practice. And here my conclusion is, the personal conclusion at least, is that the prior on the semi-amplitude and on the period have a particularly significant impact on the statistical significance of low amplitude planets. And it's really not surprising, because if you expect that there are small planets, then your prior is going to push the detection of the small planets, because at this level, the likelihood is not very constraining. You will see the prior information. And on the period, it's the classical problem, it's the classical feature of statistical analysis in general, is that if you search something into more models, then the probability that you're going to find something by chance increases. So you want to penalize the fact that you have searched in a wide variety of models. So the wider your period range is, the wider your semi-amplitude range is, the more you're going to penalize the detection of small planets. Okay, so now for the decision problem, I will focus on my own work. And so where we start is the following. So we have a radial velocity time series, we have indicators, we have done our reduction job. We have our noise model. We've done the modeling. We have a certain model or a collection of models. So maybe you can say that the data is explained by a stochastic harmonic oscillator kernel, or a Matern 3.2, or a quasi-periodic kernel, but you have a box of acceptable models. And you have your priors for the model parameters. And so the question I tried to answer is, so based on that, what is the best exoplanet detection criterion that we can think of? So the way we detect exoplanets usually is, so at least historically, the first method proposed was a periodogram, which has the advantage of being fast. And the principle of the periodogram is that you have a grid of frequencies here. And at each frequency, you're going to fit a certain model with a periodic signal at this frequency. In most cases, the model is sinusoid, but you can also generalize it to a Keplerian model. And then you're going to compare the model without and with planet at omega and look where at which frequency you explain the data the best. So in the Lomskergel case, so for example, with some of my colleagues, the case we considered is the null hypothesis model is a Gaussian noise with a fixed covariance, and your alternative model is a sinusoid plus a noise with this same covariance. And then what you want to compute is the probability to have a peak at least as high as the maximum under the null hypothesis. But the problem is, like here is an example where I injected 3 planets in red, and the maximum of the periodogram is not on any of these ones. So it's because we searched 1 planet at a time. If we want to search for several planets at a time and having a more principled model comparison technique, we can compute the base factor. So we average the likelihood for an n planet model. We fix the number of planets, it's n. Then we try every combination of parameters which have n planets, and on average, what is its likelihood? And then you compare n+1 versus n planets. But this is very computationally heavy. So sometimes you will use a periodogram because it's faster, because for some reason you don't have the time to do the full Bayesian analysis, or you want to explore a particular aspect. Okay, so one thing you can do is to compare the existing detection criteria. So here I did a simulation with 1,000 systems with 0, 1, or 2 planets. I'm going to compute the base factor, the periodogram, and so on. And I'm going to vary the detection threshold. So as I vary the detection threshold, so for example, here I'm becoming more and more stringent. It corresponds to raising this detection threshold as I move right. I will have less and less false detections and more misdetections, obviously, because there will be real signals which are small and which I will miss because I want to be so sure about the detection. And you can do this for the periodogram plus the false alarm probability, the base factor, and so on. And then as you move the detection threshold, you will have a certain number of false detections and a certain number of mistakes, false and misdetections. And if you plot one against the other, so as I move my detection threshold towards being more and more stringent, I will have less and less false detection, but more and more misdetections. But okay, so can we do better than these existing criteria? So there are 3 questions. First, what would be the optimal detection criterion? If once we have the problem, does the optimal solution exist? And if yes, how does it perform? So where I'm starting from a likelihood. I have done my modeling, I have done my reduction, I have the data, I have the likelihood. So now my likelihood so here is the data. Each planet is characterized by a set of orbital elements, and I have other parameters like offset, strands, hyperparameters of a Gaussian process, and so on. So we define a detection claim as, so what I'm calling a detection is saying, based on this particular data set, there are n planets. This planet with an orbital element in this region of the parameter space. So here the parameter space is semi-major axis planet mass, and I'm saying there is one planet here, and there is another planet here. So, but I can generalize the setting and saying, well, I have n patterns. I have a parameter space. I have 2 patterns here. The first pattern has parameters in this region. The second has parameters in this region. So that's what my detection claim is. And in the particular example I will use, I will just say that I have detected a planet when I have an frequency interval, when I have an uncertainty on its period. So here I have detected 2 planets, one with a period in this range, one with a period in this range. But now I could say that there is a Jupiter at 100 days, there is an Earth at 3 days, there is a Venus at whatever orbital period, but all the different detection claims are not equivalent. Some of them are better than others. So how would you rate if a detection claim is good or not? So let's suppose that here I have said that there are 2 planets, and the first planet has a frequency in this interval, the second planet a frequency in this interval. But in truth, there are 3 planets, one here, and one here. So this one, I got it. It's a correct detection. Good. I say that there is 1 planet here, but there is none. So I have 1 false detection. And these 2, I have missed them. So they are misdetections. So now, if I want to optimize my decision, I want the decision which maximizes a certain utility. And my utility is the expected number of false detections plus a certain cost ratio, gamma, times the expected number of misdetections. And I can look at the problem in another way and say, well, I have a certain false detection budget. I don't want too many false detections. And for all the criteria which satisfy this criterion, I want to maximize the number of true detections, or equivalently to minimize the number of missed ones. So this formulation is very close to what in statistics is called a false discovery rate problem. And when I'm talking about expectations, it's expectation on the posterior probability of the elements. Okay. The problem is posed, we have our setting, we have an optimization problem, and we know on which space we are trying to optimize. So now the solution involves a little bit of math, and once you've done the reasoning, the solution is very simple, in fact. You take your frequency interval and you slide it across the orbital frequency range. And at each center of the interval, you're going to compute the probability that you have a planet in there. So here I move, and the yellow curve, the probability that there is truly a planet in there, true inclusion probability, is 1. And here also. Well, 1, not exactly 1, because now if I take 1 minus the true inclusion probability, and I compute its logarithm, here I see it's 10 to the, so minus the logarithm is 10 to the minus, is 10 to the 12. No, it's 12, sorry. It's minus the logarithm is 12. So the probability that there is no planet is 10 to the minus 12. So it's exactly like a false alarm probability where you compute the probability of the null hypothesis. Here, the probability that there is no planet is 10 to the minus 12. So it's very clear that there is one. And so the way you would compute this probability to have a planet, in fact, is very simple. So this is the probability I want to compute. It's the probability that I have a planet with orbital elements in this space theta. So I'm going to chop my parameter space into space where I have a fixed number of planets, k. And I can compute the probability to have k planets. It's just basically I need to invert the Bayesian evidence. It's just the base formula. So if I know how to compute the evidence, I know how to compute this. Now, for a fixed number of planets, I want to compute the posterior probability that I have a planet in there. So basically, I want to compute the number of samples that I have where one of the planets has a frequency in there. And again, it's something that you can compute fairly easily, especially from nested sample, or not especially, but in particular from nested samplers. You just look at the samples where there is a planet in there, and you compute the sum of their weighted likelihood divided by the global evidence of your model. So if you know how to compute the evidence, you know how to compute the FIP, and I'm going to put very shortly a notebook on my GitHub page to show an example of how you can do it, but it's really a few lines of code. So now if you compare the FIP to the, so let's go back to the simulation, and you see that you gain 30% more true detection than the other detection methods. Yeah, so now if you, an important test that you can run is if you change the prior. So I generated the data with a certain distribution of semi-amplitudes or period. So, and to do the analysis so far, I used the same prior as the one that I used to generate the data. But in real life, you don't know what is the true statistical distribution of exoplanets. So I'm generating the data set with a certain prior, and I'm analyzing it with another one. And here you see that the number of mistakes, so this is just by the different colors is just by changing the prior. And the number of mistakes compared to the nominal model, when I have the priors right, can rise pretty high. And it rises so high that it kind of reaches, it reaches another method here in gray, the L1 periodogram, which is something else that I did. And so I'm not going to the details. I just want to make the point that the code is public now and that you can use it on days. So if you want to try the L1 periodogram, you're welcome, and you can send me an email if you have a problem. So now, there's a missing slide, but never mind. Okay. There is an interesting problem that I think has not been treated yet in the exoplanet community, or not really explicitly, and it's the following. It's when we compute a base factor, when we do a model comparison, we compare models to one another. But implicitly, we have a box of acceptable models, and we are comparing them. But the problem that you have is that maybe this box of models is wrong. And it's something that the statistician George Box described in a 1980 paper. He said, well, you have the estimation problem. Estimation problem is I have all my different hypotheses, and I want to choose the best one among them. And I have the criticism problem, which is I want to see if the box of models that I chose is realistic or not. So the method that I suggest is based on the predictive ability of your model. So suppose that you have data taken between -100 and 100 days. And you know that 100 observations are going to be taken from 0 to 100 days. So exactly the same observation pattern. And you're going to predict to sample from the predictive distribution. Well, the data could be this, or it could be this, it could be this. And in that particular example, I have one planet plus some correlated noise, I guess, I think. And for each of these predicted, for each of these sample, I'm going to compute the Fourier transform. And here, since it's evenly sampled, I'm going to use the FFT, and I'm going to report the coefficient amplitude of the FFT. And so as I generated millions of these expected data, I will have some confidence intervals. I know that the coefficient should be roughly here in 90% of the cases. So now I can count how many samples for a particular simulation fall out of this 90% predictive interval. And I can have a statistical distribution. So I know that on average on all the 100 Fourier coefficients, I will have 5 which fall outside of the 90% bounds. But now I have the real data. And I can do the Fourier transform and plot where the Fourier coefficients are compared to this 90% interval. And in that case, I have 12 coefficients which are outside of the bounds, and I see that it's very unlikely if the model is correct. So with this particular predictive test, I can try to see if the the models that I consider to compute this predictive distribution are realistic or not. Okay. Yeah, I'm not going to talk about that, but so in conclusion, so I think from our review with Eric, and so feel free to disagree, Eric, but I think one thing we need to explore and is to utilize color-dependent information on the spectrum, because now we have a fairly good idea of what it's like to look at the variation of the CCF of the either with the full width half maximum or with principal components. We're trying to determine how the different colors, what are the group of frequencies of lines corresponding to certain frequencies which move together or not, is something that we need to explore. How to reduce the information from the spectrum, where is the information of the spectrum, and how can we reduce it to indicators, is also something that we need to evaluate. And something which seemed very important to us is how to validate our method. And so this pertains also to how we will build the new data challenges for the community. And so we suggested 3 ways forward. The first one is simply Bayesian model comparison. So you compare your different models of stellar activity and see if there is one which is favored or not. So that's fairly straightforward. The second is to evaluate the predictive ability of your model. So here it's not comparing models to one another, but as I said before, it's to evaluate the model in an absolute sense. Is it able to predict the data or not? And finally, we can do injection recovery test, but the tweak that we suggest is to use a kind of receiving operator characteristic curve, just like the one that I showed to evaluate the performance of the FIP. And here you compute the number of false and miss detections as a function of the number of false detections for different thresholds. So you get rid of one possible difference between methods, which is that different teams, they might have exactly the same method to analyze the data, but they choose different thresholds. It's not really relevant to determining what method is the best. So obviously, it will be very important to use the solar data from different instruments to see if the variation comes from the star or from the instrument. That's fairly obvious. And there are also some data sets where where you have, for example, a giant planet on an eccentric orbit, and you know that there cannot be planets like a planet inside the orbit of the giant planet would be unstable. But in any case, I think it's very important that we move the data challenges towards real data. On the FIP side, as I said, there will be soon a notebook to explain how to compute the FIP. And so if you have any questions, feel free to contact me. And another important thing is if you see a mistake in the review, you can send me an email, but you have to do it this week because I have to send the proofs very shortly. And I thank you for your attention.
Fantastic. Thank you so much for that excellent overview and talk, Nathan. Yeah, lots of clapping hands emojis in this Zoom participants list. So clearly folks are excited. I'd like to open the floor up for questions. So please feel free to raise your hand via Zoom and I'll call on you, or put something in the chat and I can read it out, whatever is most convenient. Okay, well, people ponder, I can start. So for the FIP method you're talking about at the end, are there any circumstances like where you would want to be wary about using that, or is it a general purpose, should work on any and all data sets? Sorry for the dog.
This one?
Yeah.
Well, I don't know. I think I need to try it on or you can also try it, but for the moment it's just an idea, a principle, and how it works in practice, how it can be used, whether it's useful or not. it will have to be decided with examples. Yeah. But
Okay.
I mean, my point was more conceptually, this is something that is not done. So
Sure.
let's explore this direction.
Okay. Other questions from the audience? Okay, and so the review paper is available now, proofs going in soon. So if anyone scans it in the next week or so, they get back to you with comments.
Yeah. Yeah, well, I have to, yeah, as I said, I have to send the proof very soon. So yeah, if you send me an email today or tomorrow, I can still change something. But yeah, it's really at this stage of the publication, it's really about the mistakes. So if there is something which is wrong, it's time to change it.
Given all the care that I'm sure you and Eric poured into it, I imagine it is in excellent shape already.
Yeah.
Okay.
Yeah.
Well, if there are no other comments, yeah, Eric says in the chat, a big thanks to Nathan for leading this effort. I'm honestly just astounded at the number of citations that you managed to pour both into the main document and the appendixes that you mentioned. That is,
well, yeah, there are probably 250 different citations or 200, and it's still not enough to cover everything. So I was kind of surprised that the field is this big. It's really big, in fact.
Yeah, it says a lot for how much it's developed over the last few years to decades.
Yeah.
Okay, well, there are no other questions in the chat. Let's thank Nathan again for an excellent overview of this. I encourage everyone to go and take a look at this new review article. It's really a masterpiece and worth digging into and spending the time on.
Yeah, and so I just before, thanks to Eric also,
please,
who's done a significant amount of work on the review too.
Yeah, very much so. Okay, well, thanks everyone for calling in. I hope you all have a lovely holiday. We will be back in January with the next talk in our series. We're still finalizing the speaker for that. And as a heads up, I'm hoping to get an email out about this next week. But we're also looking to hold a topical meeting, a smaller discussion, probably on January 19th, about laser frequency cones and their use in a variety of EPRV instruments right now. So we're trying to put that together, and I will have information out about it probably in the next week or so. But yeah, thank you all so much for calling in. Have a great rest of your Thursday.